Hi everyone, in this video we're going to work through a fairly big example. It's an application involving a quadratic function, and what I'd like to work on first is if I give you the quadratic function, can you answer a whole bunch of questions based on that? We'll also work on, given a description of the situation, can you create the function, the equation yourself? So that's coming, but in this example I've given it to you. So this right here is my function. This function inputs the size of the population, the number of deer basically, in a national park, and it outputs the expected population increase that year. So if you know how many deer are living in the park, this is supposed to predict how many additional or how many fewer deer you'll have the next year. Okay, so this is going to ask for a lot of details about the graph, and then we're going to try and figure out what exactly that's telling us about the deer population in this park. So the very first one, we want to find horizontal intercepts. And again, with this wording, I'm not trying to be tricky when I say horizontal intercepts. It's just that I don't always use variables x and y in word problems, so I want to have a more generic way to refer to them. So horizontal intercepts are going to be where you cross the horizontal axis, so they really are x-intercepts in this one. To find horizontal intercepts, you always let your output variable, your y, be 0. Do I have enough? One more, 0, 0, 2, x squared. And then you'll want to square root or factor or use the quadratic formula. A lot of people get a little stuck on this one, but this one's actually wonderful. We can factor out an x here. If you'd like, 1.2, you can try factoring out something other than that to deal with these decimals. So it's looking like I get x equals 0 or 1.2 minus 2 1,000ths x equals 0, if I can say that, which means 1.2 is equal to 0.000. I think I keep dropping one. Sorry, guys. Too many zeros. 0.0002. And then we can divide, and I'm going to go ahead and ask my calculator since I'm running out of room. 1.2 over 2, 6,000. Okay, so I have intercepts at 0 and 6,000. Again, you want to remember that that means there are points. There's an x and a y coordinate to every intercept. So this graph will go through 0, 0, and 6,000 zeros. So in my little sketch at the top, crossing the origin and here, and I know the function opens down, so I already have kind of a decent rough picture in my head of what this thing looks like. Explain the meaning in everyday language. Okay, so remember that your x here is the number, it's the current deer population. So if there are currently 0 deer in the park, the population is not expected to increase or decrease. So apparently nobody's moving into the park. If there aren't any deer, there won't be a population increase. The one on the other end I think is a little more interesting. This says if there's 6,000 deer, the population won't change, won't increase or decrease. So something's happening on that end as well. And that's all I'd be looking for with the explain their everyday meaning. So if there are no deer, the population won't change. If there are 6,000 deer, the population won't change. Next, we want to find the vertex and explain its meaning in everyday language. Okay, so I've already got a picture started. It's really nice if you kind of keep a rough sketch going or even check the graph in your calculator just so you've got a little visual on this. Vertex. So in this one, my x-intercepts are really nice and easy. So there are a few tricks we can use to find vertex. Right now, I would say the easiest one is halfway between my two intercepts is x equals 3,000. So the x-coordinate of the vertex has to be at 3,000. That's in the middle of my two intercepts. To find the y-coordinate, I would just plug it back in. So I of 3,000 is 1.2 times 3,000 minus 0.0002 times 3,000 squared. Okay, so 1.2 times 3,000 minus 0.0002 times 3,000 squared. Okay, so we're getting I of 3,000 equals 1800. Okay. And then explain its meaning in everyday language. So this is saying if the deer population is 3,000, then we would expect the population to increase that year by 1,800. So that's the kind of most crucial information, but there is another really important detail that I would want you to be keeping track of, and that's the fact that this is a vertex. So this should either be a maximum or a minimum y value. In this case, it's a maximum y value. So again, back up in my little picture up at the top. This is saying that if the deer population is 3,000, we will see the maximum expected increase of 1,800 deer. There's no other base population that would lead to a higher increase in population. So they are really busy that year. I don't know that this is necessarily realistic numbers. This is totally made up, but that's what that's predicting. Okay. Part C, we want an average rate of change from x equals 0 to x equals 3,000, and then to explain its meaning. So remember, average rate of change is just slope. So we have 2 points. When x equals 0, y is also equal to 0. And when x equals 3,000, y is equal to 1,800. So we're getting off a little easy here. We've already found both y coordinates. If you didn't have those, you'd have to do the work to plug your x's in to get a point. So we are getting 1,800 minus 0 over 3,000 minus 0. Let's knock off a couple of those. So we have 18 over 30. So 6 over 10. You can ask your calculator for this as well. Well, it's not even approximate, which is 0.3. Oh, 0.3. What am I saying? 3/5. 0.6. There we go. Okay. And then we're supposed to explain what this means. So I'm debating if I really like the 0.6 best or not. I actually think I might change my mind and say I went 3/5. I don't know that I want to talk about a decimal part of a deer here. So I'm thinking the 3/5, which is where the 0.3 was coming from. I was thinking about both. The 3/5 might be the nicest. This is a really kind of tricky one to explain the meaning of, so I will give it my best shot. Okay, so there's a lot of information floating around in the average rate of change stuff. It is a slope, so we can interpret this as a slope. If the base population has 5 more deer, then the predicted population increase will go up by 3. So that's what that's saying, but the additional information is the fact that that's approximate. That's definitely not something I expect to be perfect. This is not a linear function. This is a quadratic function, so it's not going to perfectly follow that slope. Although you can see if I draw in that line through those 2 points, it does a decent job of predicting what's going on between 0 and 3,000. And that's the other key piece of information, is that this is only good if you're talking about deer populations between 0 and 3,000. So I'm going to try and put it all together. I would say if the deer population is between 0 and 3,000, adding 5 deer to the base population will increase the expected increase, I don't know if I like that very much, by 3 deer on average or approximately. Let me see if I can think of any better way to say that. I'll try once more, so I don't know if it's going to be better or worse. So again, if the base population of deer is between 0 and 3,000, adding 5 deer to that base will add 3 deer to the predicted increase in population. I think that was a little better. Again, on average or approximately should be in there somewhere. Okay, let me know if that one mixes you up. That's always a tricky one. I like to do messy ones in my examples, but that one is a tricky one to word. All right, I'm asking for a sketch down here. We've already done most of that, and I don't say it here, but you do want to think a little bit about reasonable domain. I have some more questions that are going to lead us to that. So there's my rough sketch at the top. For now, I'm just going to reproduce it. Whenever we're working on a word problem, we really only want to see what's reasonable, but I think that's a really tricky question here, actually. That's one of the reasons I like this kind of silly made-up problem. Okay, so this is at 6,000. This is at 3,000. And this is the x-axis. And we can call this, what did we say, y equals I of x. So you could call it I, or you could call it y. I'll go ahead and call it y since it says y is our output variable. You can also label those axes with words. So you could say, in this case, actually, I don't love that because it would be deer and deer. So this is base population of deer, and this is the increase in population of deer. So I think I'll stick with my variables. So there's our rough sketch that we had. On the reasonable domain, I actually think this is a little tricky. I don't think we can have a negative base population, so I have cut it off carefully at 0, 0. But on the other side, a lot of people want to immediately say you can't have a negative y value. And I don't know that I believe that. The y value is supposed to tell you how much your population changes. So you could have a population decrease, and that's what I think this is trying to tell me. If there are more than 6,000 deer in the base population, then the population is actually going to decrease. So the last couple of questions are just to play around with this a little bit. It's kind of an extra tricky one on the domain stuff. So there's an intersection question. If y equals x, y equals negative x, if we put them on the graph, can we figure out where they cross and what that tells us? In fact, I don't even ask where, I just ask what it would mean, but we can figure out where. Okay, so if this is 3,000, 1,800, 3,000, 3,000, I think it does cross. So they definitely cross at 0, 0. And then I think that y equals x will cross somewhere else. Not entirely sure where. This isn't a perfect picture. And then this isn't going to look great. But if I drew y equals negative x somewhere way out here, I would expect to see another intersection. So if we would like to find those, the algebra is actually not very hard. I'm going to put it up here so that it fits. If you want to find where any two curves intersect, you can just set their equations equal. That's just claiming that their y's are going to be equal. So we would set the x equal to our original 1.2x minus 0.0002x squared. And then you could subtract an x. We want to set this equal to 0. Okay. And then we could factor out, in fact, I'm really tempted to, I'm going to multiply everything here by, you don't have to, but I kind of like to clear decimals. So let's see, 1, 2, 3, 4. So we'd have to multiply by 10,000. Okay, so this is going to stay the same if we're moving this. Oh, I'm sorry, I'm still writing the same thing. Decimal over 4 times, there's 1, 2, 3, 4. 1, 2, 3, 4. And then we could factor out a 2. So not required that you clear out decimals, but I think it actually is kind of nice. You have a calculator, so if you just want to deal with those numbers, you can. Oh, let's factor out a 2x while we're at it. Okay, so it looks like at x equals 0, which we already predicted, or x equals 1,000, we get an intersection. And we could do similar work for the negative x. Actually, yeah, I'll go ahead and do the work, debating if I want to have a specific number. Squared. Okay, so if we add an x to both sides, add an x, this is going to be 0. We're going to get a 2.2x minus 2 10,000ths, I guess is what that really is. And then I'm going to go ahead and do the same thing. Move the decimal place over 1, 2, 3, 4 times. And then x squared. Factor out a 2. Factor out a 2x. Man, see if I can get these right today. So it looks like x equals 0, which again we predicted, or x equals 11,000. Okay, so we have the point 0, 0. They all cross through. We have the point, which was this one, 1,000. And that one should be really easy to find the y-coordinate of. This is supposed to be y equals x. So whatever your x-coordinate is, your y-coordinate is exactly the same. And then this is y equals negative x that we're crossing. So whatever your x-coordinate is, your y-coordinate should be the exact opposite. Okay, so lots of work there. We're supposed to talk about what those points mean. And what I'm really looking for, yeah, so I even say it there. What is the significance of the intersection? So what's special about these points? So 0, 0, I don't think really shows it, but I'm really interested in the 1,000, 1,000, and the 11,000, negative 11,000. So 1,000, 1,000, that's saying if there are 1,000 deer in the park, the expected population increase is 1,000. So I would say that year is interesting. And again, this may or may not be realistic, but that's saying your population is going to double. So we're getting lots of new deer if the base population is 1,000. If the base population is 11,000, the population is expected to decrease by 11,000. So this is like deer apocalypse. If there are 11,000 deer in the park, they are all expected to die. So I'm not claiming that this is a super reasonable number, but I would just say that this one is kind of a tricky one on the reasonable domain. I don't think we should just cut it off at 6,000 because I actually think it makes a lot of sense that maybe this is some sort of carrying capacity, 6,000. So if you have more than 6,000, the population is going to drop. If you have less than 6,000, the population is going to increase. And actually, if you play around a little with plugging in numbers, you'll find that if you're a little below 6,000, you jump a little above. If you're a little above, you drop back down a little below, and it kind of ping-pongs and gets you really close to that 6,000. So I do think we're seeing some sort of carrying capacity of the park here. But again, that doesn't mean you can't go over that. That just means if you go over that, the park can't support all of the deer and the population will drop. So I would say that in terms of where you should cut it off, definitely at 0, 0. We don't want to see anything left of that. The right-hand side is a little bit more open. I think it should be bigger than 6,000. And I think it should definitely be at most 11,000. After that, you're getting more deer dying off or disappearing from the park than there were in the park in the first place. So this is the absolute extreme end of what could possibly have any good meaning. So I'm just going to leave you with that. I'm not going to give you an answer. Again, I think the idea with reasonable domain and range isn't that there's one correct answer. That's not what I'm going for. I'm also not going for you to all be experts on deer or whatever the problem is about. But I do want you to think about those little details, like, do I really cut it off at 6,000? And I think the answer here is no. Okay, I think that's it for that long one. Thanks for watching.